Yes, sir.
Okay, recording and transcription. Okay, cool. So thank you for inviting me, for giving me the opportunity. Thank you for finding the time, almost at lunch, to hear about White Rabbit. So my name is Maciej Lipinski. I work at CERN, European Organization for Nuclear Research, and also I'm part of the White Rabbit collaboration that is basically transferring the technology that we develop at CERN to wider audience and to the industry. So today's presentation is, we call it informally White Rabbit for Dummies. I hope this is no offense to anybody. It's just that this is like we try to make the series of books for dummies, meaning people who are have no expertise in a domain and still want to understand basics. So that's the idea, to have to develop a presentation for people who have no expertise and still want to know how the things work at the higher level. So we, to speak about White Rabbit, we need to speak about synchronization, what it is, and what is the importance of synchronization in the world, uh, in the industry, and for us as individuals. So first of all, we are speaking about synchronization between devices which are interconnected. And by synchronization, we mean that they show the same time at the same instant of time. So you can see here two computers that show, let's say, at the screen a time, and this time seems to be the same. And this is what we mean that they are synchronized, that they show basically the same time. However, the level of synchronization is also important. So we can display also a digital clock in these devices, and we can instantly see that they are synchronized within a 1 second, meaning that they are off by 1 second. Because one is showing 1150, the other is showing 1150 and 1 second. And this is what we call the accuracy of synchronization. They are accurate within 1 second. And for some applications, it is more than enough. And for other applications, it is very bad, let's say. So just to give you a scale of accuracy of synchronization that we are speaking about, 1 second for devices is quite a lot. Actually, but this is something that actually a human can comprehend. 1 second is more or less that, but we will be speaking about much shorter times. And to give you some kind of an idea of what is actually a millisecond, microsecond, nanosecond, I try to make a comparison. So in 1 second, the light travels from Earth to Moon, roughly. In 1 millisecond, it goes from one end of Switzerland to the other. In 1 microsecond, it traverses 3 football fields. In 1 nanosecond, it traverses the length of the foot. And in 1 picosecond, it will go the length of the width of the syringe, so very short distance. Okay. And actually, at CERN, we are measuring a distance in nanoseconds. So each of our cables, I have a cable here for the oscilloscope. It has a label which says how many, I don't know whether you see, okay, we'll not see, but it says 6 nanoseconds. So this is basically the length that we are measuring things in time, in nanoseconds, not in meters. And this means that in 6 nanoseconds, the electrical signal will traverse this cable. So then how this translates into industry, into basically our life and so on. So with this graph, I'm intending to show the evolution of synchronization needs and importance in relevant technologies and industries. So for appliances that we are using every day, the need of synchronization is around 1 second to 1 millisecond, depending on what type of appliance we are speaking about. And you might not be aware, but actually time is critical to operation of most of the equipment that we are using, appliances. To make a bank transfer or to pay with a credit card, we need time. If we have CCTV, we actually rely on time to know what is the sequence of events, and so on and so on. So it's quite important, but the level of accuracy is quite low. Now, time is also important, for example, for finance. And until the financial transactions were made by phone, nobody really cared about time. But as soon as they started going digital, they started caring about time. And in recent times, there has been two major events. One is introduction of MiFID, so basically EU law, which has equivalent also in US, which obliges the financial institutions to have traceability to some accuracy, and this is needed for auditing the transactions. And then high frequency trading, which is basically an automated trading that happens super fast, and these guys are caring about nanoseconds. Another industry that cares about time a lot is telecommunication. So again, the operation of our mobile phones depends on synchronization, and until 2010 or so, so like 1 decade ago, it was mostly about frequency synchronization, but recently, especially for 5G operation, time and frequency are super important, and the requirements are getting more and more stringent for this industry. Another industry that cares about time more and more is power industry, and this is for synchronization within the substations, but also between the substations. And the synchronization here is important for two reasons. One, with a proliferation of home production of power, the phase of how the power is injected into the grid makes a difference, and it needs to be coordinated. And also for fault detection. If we synchronize different substations, we can detect where is the fault very, very fast. Another place where time is becoming more and more relevant is data centers. And this is both synchronization between the data centers and within data centers. Between data centers, the synchronization became super important when we started having distributed databases, like for Meta, for Amazon services, and so on, where actually the same data can be held in different data centers across the globe. And we need to figure out which data is the most up to date. And this is done through timestamping of the data. And then very recently, Meta realized, and others, that actually by synchronization, very fine synchronization within the data centers, they can save a lot of money. And this can be done in two ways. One, by speeding up the algorithms, which needs to coordinate computations in different machines. And then the other thing is that if you launch, let's say, very powerful computations at the very same time, your power consumption spikes. If you distribute it over time, the power consumption will be more evenly distributed. So there's a lot of savings by just synchronizing computations in data centers. And finally, science is working with physical phenomena, which very often happens at the speed of light. And as you know, the light traverses in 1 nanosecond, 30 centimeters. So in principle, we've been caring about fine synchronization at nanosecond levels for long, and now we need even more. So this is just to give you some idea of where and how time is important in the world in different industries. And this synchronization is covered by different technologies for different industries and level of synchronization. So we have the network time protocol, which is used by all the appliances, even if we are not aware of that. Basically, we use NTP every day for operation of different devices that we are using. Now, GNSS, so GPS, Galileo, and so on, also provide time. So the satellites provide not only the localization, but also time. And this is used by a lot of industries. So a lot of industries rely on GNSS for synchronization. However, GNSS is not perfect for many reasons. One of them is that you cannot have antenna everywhere. So there is another protocol that is complementary somehow to GNSS, is PTP, Precision Time Protocol, that provides network synchronization. And then what we'll be speaking today about, and for which we have this long introduction, is the White Rabbit, which is the technology that we have developed that provides below nanosecond level of synchronization, and that has been incorporated in the Precision Time Protocol. So now, basically, you can see that this PTP is joining with what used to be White Rabbit. And what you can see also is this tendency of different industries to rapidly require more and more precise, accurate synchronization, which basically translates into money for them. So this is something important to keep in mind for later. Now, we are speaking today about White Rabbit, so a bit of history and background how White Rabbit came to life before I explain what it is. So White Rabbit is a project and a technology that was developed for high energy physics, so physical experiments in such places as CERN, where I work. And it was meant to be a next generation control and timing system. And this here maybe it's important to explain how this kind of experiments, especially accelerators, work. And what is super important is to understand that we have very big facilities. So CERN, the biggest accelerator at CERN, has 27 kilometers circumference, so it's long, 27 kilometers long. It's a huge area, and in this in the accelerator, the beam travels at the speed of light. Actually, the electrical or optical signals that can be used to control devices that make sure that the beam behaves well and produce beam, those signals travel at the 2/3 of the speed of light. Meaning that if we just want to control these devices in a classic way, where basically a central controller is telling them what they should do, the time of traveling from the central controller to different devices makes a huge difference and prevents us from scheduling events at the same time. Because, for example, if to travel, let's say, if one device is close to our control and the other is at the other end, the difference in distance is 9 kilometers, which translates into many microseconds of time just for the signal to pass. And in this time, the beam will make many circles around this 27 kilometers. So how controlling accelerators is solved is that all the devices across the accelerators are synchronized with very good accuracy, around 1 nanosecond. And then these devices are programmed in advance what they should do at a given UTC time. And then basically they do whatever should be done at UTC time to within nanosecond. And in this way, regardless of the location of the devices, we can trigger some actions at the very same time to within nanosecond. And this is why we need White Rabbit. So White Rabbit itself is a project that started as a collaboration in 2008. And immediately we realized that our needs are shared by other facilities, scientific facilities, like the GSI in Germany, or a super nice experiment that is being built at the bed of Mediterranean Sea, which is 1 cubic kilometer detector of neutrinos that is attached to the bed of the Mediterranean Sea. It's called KM3net. So we, let's say, hooked together to work on common needs. And the initial specs of White Rabbit were to base it on the well-established standards. And one of the reasons to do that is that the lifetime of devices in such facilities as CERN or GSI is enormous. It's like 30, 40 years for the devices to work. And they become obsolete even before they start being operational very often, which is a problem for us. So we figure out that if we base the system on a well-established standard that will basically live long, like Ethernet, that we have been around for long and is going to stay, we, let's say, prolong the support for this technology. Another requirement was, of course, to have sub-nanosecond synchronization. Deterministic data transfer, I will not go to it, but it's a point here. And then, because of the size of CERN, the initial specs were the links of 10 kilometers and up to 2,000 end stations, so the devices to be controlled. It should be plug and play, and what we mean by that is that the predecessor of White Rabbit is an old system, and in this system, actually, each time we restart the machine, we need to go to each of the 2,000 devices with a cesium clock and by hand adjust the delays. It's a super time-consuming exercise that we wanted to basically not do anymore. So by plug and play, we mean that we just plug the device and it gets a sub-nanosecond without any further additional work from our side. And another very important feature is to be open source and commercially available. And this is something that seems to be contradictory, but actually we merged the two. So we work on open source devices that we design ourselves, and then later we buy them from companies. And then companies are free to sell them to others and to innovate and so on. And this is one of the reasons why Rabbit also is being spread in many different applications. So this is the genesis of White Rabbit. Now, how does it work in a nutshell? So it's super simple. It's this equation which says that White Rabbit is basically the PTP, precision time protocol, layer 1 synchronization, phase detection, and asymmetric collection. And that's it. So now you know everything. But if you go a bit into details of each of these elements, you might not be familiar with PTP, so I will briefly explain. Precision time protocol is an industry standard that allows to synchronize different devices over a network. And this can be different types of network, Ethernet network, or even over air. And the basic mechanism of how it works, it exchanges messages. So one device sends a hello, I'm here message, which it time tags with the time with the time at which it sent the device. It sent the message. So it can be any time. It doesn't. I mean, it's just its own time that he knows. And when this message arrives to the other device, this device is timestamping the time of arrival of this message with its own time. So those are called timestamps. And at this point, the time of one and the other device can be completely off by years even. It doesn't matter. And then the same happens in the other direction. So the device on the right sends a hello, I'm here message to the device on the left, and also logs the time of its transmission, the message, and the other one logs the time of the arrival. Now with these 4 timestamps, we can actually correct the time of the device on the right to be roughly the same as the time of the device on the left with a super simple school math. So in essence, we calculate what is the difference of time between T1 and T4. So how long it took to have the round trip. Then we subtract the time it took on the other device, so T3 minus T2, to basically to go back with the message. And if we divide this by 2, we know the one-way delay from the device on the left to the device on the right, and we can correct the time. Now, this is basically how PTP, so precision time protocol, works. And it works perfectly to up to accuracy of roughly 1 microsecond. And then when we want to do better, we find some problems. And we identified 3 limitations of PTP, which is one is the fact that the clocks on one device and the other are free running, meaning that between the exchange of the messages and also during the measurement itself, one can drift with respect to the other. That means that basically between the corrections of time on the device on the left, the time will be getting bad. So we need to basically tune it each time we exchange the messages. And the better we want to have the accuracy, the more often we need to exchange the messages, and we hit some limits here. So basically, this is free running oscillators. If you use IQD oscillators, it might be less of a problem because you have good oscillators, but then it might be more expensive to make this device, right? So there's a trade-off. Another limitation is the symmetry assumption. So in the simple equation, we assume that life is perfect, which is never the case, and there are everywhere asymmetries in the world, and in particular, the medium itself might be asymmetric. So the time of travel in one direction from left to right might be a bit different than the time of travel from right to left, which will introduce an error in the time correction. And then also the timestamps themselves, they have finite resolution. So basically, you make a snapshot of the time, but we are not sure to within some nanoseconds what is exactly the time. So we corrected all those limitations, and we started with the frequency with the free running oscillators. So what we did is basically use the fact that when somebody is transferring data over a link, this data carries not only zero and ones, which translate into words and images, but it also has embedded frequency, because you need to encode the 0 and 1s with frequency. And in standard Ethernet, this frequency basically is discarded by the receiver. It is used to recover the data, but then it basically is discarded. So what we decided to do, and what is actually done also in telecom, we recovered the frequency from the data. So imagine that the guy on the left is sending data, and the data has in it inherently it has the information about the frequency. The data with information of frequency is received by the device on the right, and then with the data we also recover the frequency, and the device on the right is actually using this recovered frequency to run its own clock. So at that moment, both devices are working with exactly the same frequency, and that means that they will never drift with some caveat, but let's say the first approximation, they will not drift between the exchange of messages, so between the measurements and during the measurements. So this kills the first limitation of precision time protocol, and it enhances the precision with which we can measure the correction of time. Then the next limitation was not the same order, sorry, to correct, but another limitation is the resolution of timestamps. And then typically how the timestamps are done is that we have a clock, which is a counter that is incremented with the frequency of our internal clock. So in other words, in our case, to be very precise, we increment our clock with 16 nanoseconds increments. So every 16 nanoseconds, you add 16 nanoseconds. And that means that you cannot measure the time more precisely than with 16 nanoseconds resolution. And this is typically the case for any other device. So in principle, the typical resolution of timestamps in network devices is 8 nanoseconds. And if you really stretch it, it will be 1 nanosecond. But that's it. You cannot really do better with classical timestamping. But what we actually did is use phase detection techniques. So since we have the same frequency on both devices, that means that we can use phase detection to detect the phase between the clock, the frequency on one device and the other. So phase detection techniques, if you look into it, they allow for very much finite precision of measurements. And our technique that we are using, that we actually invented at CERN, and we are very proud of that, is allowing us to detect the phase with picosecond precision. So we effectively increase the resolution of timestamps from 16 nanoseconds to few picoseconds. And this allows us to make the measurements that are done by PTP with picosecond precision. Then the next thing that was a limitation was this assumption that the world is perfect, so everything is symmetric, which is not. And to mitigate that, we basically do a few things. First of all, we use single medium. So very often, if you have networks, two fibers are used for one direction and the other. So this is basically a standard in the telecommunication. And this means that actually these fibers can be of a different length. And remember that 1 picosecond is a syringe, and 1 nanosecond is 30 centimeters. So if you have 1 centimeter of difference of one fiber with respect to the other, you introduce picoseconds of inaccuracy. So we are using one fiber, and then we introduce a simplistic model of the entire link where we model all the asymmetries. And I will not go into details of that, but the point is that we identify different asymmetries of the devices and the medium itself, and we model it and calibrate or estimate what are the values. And those include such things as the wavelength, what the difference in wavelengths of the transmission on the fiber, the PCB traces on the device. So this device is a switch which has many centimeters of width. So depending on to which port you connect, you can have many picoseconds of difference. So we need to account for all this stuff if we want to go to nanoseconds. And this is what is done. So it's with this, we can actually synchronize the two devices with precision with accuracy of roughly 10, 20 picoseconds over one link. Now, a wide area network is an Ethernet network that consists of switches, which are the same switches as you use when you connect different computers. The only difference is that we did make them the switches ourselves. We designed them, and that they provide some nanosecond accuracy of synchronization, and stations, which call them wide area nodes. So in this network, basically, we connect one of the devices to a source of time, typically GPS and cesium clock, and then the time is distributed over a network to the end devices that use the time somehow. And this network can actually be redundant. So we can have redundant links just in case one of the links fail. The most typical failure is basically of a fiber is basically somebody is digging a hole and cutting the fiber with unintentionally, because otherwise fibers are very reliable. But in any case, this redundancy is something nice, but it is at some nanosecond level of synchronization, it is quite non-trivial to actually maintain some nanosecond during the. So we have the link that we are using for synchronization. This link fails, and we want to switch over to another path for the synchronization. And this is with PTP and protocol that we are using is quite slow to reorganize. And during this time, the performance can degrade. For some applications is acceptable, for the others is not. And this is why there's an ongoing effort to actually mitigate this problem. And one of the ways you can do it is with holdover. So what can happen is that as soon as you detect that your source of time go nuts, you switch into holdover mode. For example, using this nice holdover expansion board from IQD. And then you do as best as you can to hold the time that you know is good. And this allows for the network to organize. And once it finds the redundant path that it renders good, you switch back to synchronization to the source. And this is one of the way you can improve overall performance of the network in the case where something goes bad. The other way is seamless redundancy, which is much more difficult to implement, in which basically you synchronize to both links, to many redundant links, and then you seamlessly switch between those. Even in this case, holdover is useful in the short instant when you need to switch over. So this is basically an overview how a wide area network works and what is a link to IQD in what we are doing. Now, wide area today. So wide area today in terms of performance, you can summarize it in terms of time transfer and frequency transfer. For the time transfer at the network level, and we are speaking about network with many thousands of nodes and hundreds of switches, we can provide sub-nanosecond accuracy. On a single link, which is, okay, we have to distinguish short links and long haul links. On a short link up to 10 kilometers, the best we can provide is 20 picoseconds of accuracy. And what you can see here on the plot is actually offset between two devices, switches, which are rebooted. So basically, we synchronize two devices. We look at the offset between their time. We reboot the device. We look back at the offset between them, and we do it 22 times and even more. And you can see that essentially we always go back to offset which is below 10 picoseconds. We say 20 picoseconds because we have some outliers which go a bit farther. But the most we observed was 20 picoseconds of offset over reboots of devices. For long distance, it's a bit more complicated. We have links, wide-double links that go as far as 1,000 or even 1,800 kilometers. And if you go into long distance, then a lot depends on the technology and that you are using. So the performance can vary, but let's say up to 100 something kilometers, it is quite easy to have half a nanosecond of accuracy or between devices on a link. And I saw much better, but it really depends on the technology you are using. In terms of frequency transfer, out of the box, if you use a standard YW device, you will get 11 picoseconds RMS. We have a flavor of YW switch which is called low jitter because it gives 2 picoseconds RMS. And the best we have ever done is actually below 100 femtosecond RMS of frequency transfer. So this is the performance figures that we have today, and they may improve in the future. For another aspect of what we have today is that YW has been included into IEEE 1588 standard. So initially, YW was developed as an extension of the standard, and then it turned out that basically the standard guys found that the improvements that we did, that I explained in the previous slides, are quite interesting and useful. So we worked together for 7 years to include White Rabbit as a high accuracy profile into the standard. So now if you buy the 1588 standard, White Rabbit is just another profile of PTP. In terms of applications that we see today, there's a number of applications. Of course, in science, we see White Rabbit being used in accelerators, in detectors, in quantum, in many countries. And I just listed the ones that I know about, like Switzerland, France, Germany, US, even Mexico, and Japan. We have everywhere installations of White Rabbit for scientific purpose. Another type of application that is used extensively is the national time laboratories. So basically the institution in each of the countries that gives an official country time. And these institutions are tasked with, they have many tasks, but their main tasks are basically to give you official time of the country and also to disseminate this time to industry. So White Rabbit is used in laboratories in Switzerland, in France, in US, Finland, UK, Italy, Sweden, Netherlands, Bosnia and Herzegovina, Czech Republic, and Belgium. And now, out of those, it is important to mention that there's a planned installation of White Rabbit dissemination over the entire Belgium. White Rabbit is now disseminated around Switzerland, and they are going to sell it as a service to provide time to industry. And also, I think, where is it? In Italy, it's also sold as a service by the NMI. Another type of application of White Rabbit is to backup GPS, and this is done for telecom and data centers. So a vulnerability of, I should say, GNSS, because GPS is just one of type of GNSS. So it's quite known fact, hopefully now, and in UK is recognized officially by the country as an official vulnerability is the fact that a lot of devices depend on GNSS, and GNSS is not so safe. So there's a huge effort to actually find backups or alternatives to GNSS time synchronization, and one of them is being used is White Rabbit. And finally, in finance, White Rabbit is used also to backup GNSS, but also it's used by high frequency trading, and both on the side of the regulators to audit the transactions, but also on the side of the traders to improve their algorithms. So, for example, the German stock exchange is selling white rabbit time as a service. In Italy, the financial section in Milano is connected with white rabbit to the official time. Also in Spain or US, there are white rabbit installation for finance. And now white rabbit is commercially available from many vendors. Both we can see open source products, like the first two shelves are all open source products that are commercially available from many companies. But also we see proprietary products which are white rabbit enabled that are sold by companies. So different types of products. What would the future bring for white rabbit? Okay, I'm not I cannot tell for sure, but I know that in science, white rabbit is a de facto standard, and you can see it with the growth of installations. In 2018, we had like roughly 500 devices installed worldwide. In 2024, I would count more like 10,000 in 20 facilities. And only at CERN and also the KM3net, which is the installation on the bed of Mediterranean Sea, in the coming less than decade, we are planning to deploy thousands of devices of different types, partially already bought, partially to be bought in future. So we can see quite a huge growth in the science, which I can quantify somehow because I know this. For transfer from science to industry, in the plot that I showed initially, you can see a trend. You can see a trend that basically converges to a nanosecond in many of the industries. And this can be seen with the applications. So what you can see is that white rabbit as a service is now being more and more common at a national level. So we see it in Switzerland, in Italy, and other countries, and we know that there are ideas of actually making at least in Europe pan-European timing fiber-based network that would basically provide connect national laboratories in the entire Europe, and it might also have a dedicated timescale, European timescale, and white rabbit is being evaluated to be used in this type of network, and that would go along with the GNSS replacement and backup, because this would basically make a non-GNSS source of time readily available for industry across Europe. Finance market monitoring as white rabbit seems to become a trend in finance sector. So I see this proliferating. In telecom, we see first telecom companies starting to use white rabbit, and at ITSF there will be a presentation from Orange Poland that is deploying white rabbit. In power industry, we are working with power industry, and in quantum, which is not yet the industry, there's a lot of white rabbit applications that once quantum becomes more industrial, it will be using white rabbit. It's also important to mention the white rabbit collaboration, which IQD is a member of, and which actually has now 15 members and is growing. And the collaboration is basically meant to maintain and improve the technology which was born at CERN, but now basically grew beyond CERN. So CERN alone and the initial collaborators are not able to maintain and improve the technology due to resource limitations. It's basically we are like a victim of our success, as my boss says, meaning that there's so many requests for support from people wanting to use white rabbit that CERN alone cannot handle. So we established a white rabbit collaboration, which the goal is to maintain and improve the technology for everybody, for industry in particular, and also to look into things that in science we don't have that much experience of, which is compliance and certification, and also training and so on, foster the technology in the industry. And from the current members, you can see roughly the interest, you can see the trading companies, you can see quantum companies, you can see scientific companies. So you can see you can judge the interest and where this goes, in which direction. And I think that would be all. Maybe it was not so short, but thank you very much for your attention. I'm looking forward for questions and also any feedback for improving this presentation.
Yeah, my name's Graham. I work in application support at IQD. I just had one question. The earlier one on the PTP, is that the what they call SyncE, the synchronized Ethernet? I was just wondering how the data, how it travels over the physical layer between the two routers, say.
Right, so the question is whether basically we are using SyncE or how SyncE works.
Well, if that's what you built on, in other words, in the earlier
yes,
earlier slide.
Yeah, so it's a good catch. Yes, what we are using is let's go to the slide. Yes, so the frequency transfer is essentially the same mechanism that is using SyncE. However, we don't comply to all the different bits and pieces of the SyncE standard.
Okay.
So essentially the idea and the mechanism is the same, but then we cannot call it SyncE per se, because we don't adhere to all the different, let's say, specifications of SyncE. Yeah.
Okay.
And
it's
you can
enhanced.
yes.
Yeah.
It's a bit different in two ways. One, SyncE has its own protocol to establish the hierarchy, who is transmitter, who is receiver, which is not used. And then the second, there are some specifications about the bandwidth of the PLL and so on, which we basically tweak to have better performance.
Yeah. Okay.
And use more cheap oscillators.
Yeah.
But in essence, you can. I tested myself White Rabbit with the parameters of SyncE, and it can work with the SyncE following the standard. The only thing is that you need to use possibly more expensive oscillator.
Okay. Okay.
Grand. Any other questions, guys?
Hi, Maciej. My name's Paul. You mentioned right at the end of the slides that the intention is to build a fiber optic network over Europe on the last slide. That's wherever it is. And you also mentioned earlier on that it could be done wirelessly over the air. Is it still the intention that most of it will be on fiber, or can it be done? Can you transfer the time, etc., wirelessly, or is that not something you're pursuing?
Okay, there's many questions in this one question. So what I was referring as a pan-European network is only fiber-based. So that there are projects to make a fiber-based network, and I don't think in these ideas any over-air time transfer is considered, because basically this is to prevent any noise coming from the air transmission, because if you do over air, you can basically block this transmission.
Okay, sure.
But on the other hand, okay, GNSS is an over air transmission of time, and also you have PTP is also transferred over microwave, so you can have PTP transmission over microwave, and there has been articles and scientific research trying to use White Rabbit over microwave with no follow-ups. So there have been trials. It's not easy, and we are not pursuing the wireless transmission of White Rabbit.
Okay, that's fine. Thanks.
Liam, I see you got your hand up.
I do. Hi, Maciej. So apologies, this isn't a technical question, but where did the name White Rabbit come from?
It's a perfect question. Alice in the Wonderland. There is this rabbit that is always late. It's the scientists, they have a weird sense of humor, and this is this how it manifests.
Okay. So it
Was
came
that
from Alice in
yours?
Wonderland. Okay.
Was that you, Magic, or was that Adam, or one of the other guys?
No, it was Javier. Maybe you met Javier, if not. You
Oh,
know
Javier.
Javier.
Yeah. Cool.
We have also another project which is called Mock Turtle, another creature from. Yeah, well, yes.
You tell me
Great.
about that when we're at ITSF. I look forward to that one.
Cool. Great. Thanks.
Okay. Any other questions, guys? They don't need to be technical. Brilliant. Then I say, Magic, thank you very much. That was much more of the whole picture than I was expecting from this. I thought it was going to be a lot more basic. So yeah, I had some follow-up questions about the size of the industry, the potential size of the industry, but you seem to have covered that in this last slide. I had some thoughts about trying to explain the White Rabbit collaboration and how IQD is part of that and stuff, but I think you've covered a lot of that in this last slide as well. Yeah, so has anyone else got anything, or we'll say thank you very much?
No, thank you, Magic.
Cool.
Brilliant.
Thanks a lot for your time and
Yeah.
Yeah, thanks very much.
Thank
Thank
you.
you. Cheers all.
Cheers.
Bye.
Thank you.
Bye.
Bye-bye.